The motivation for this work is that testing is expensive, we know, and some tools can alleviate the tedious and error-prone testing activities, and one of them is test case generation, and in particular white box test case generation. That ideally it exercises, excuse me. I think I have a problem with the battery. Oh, excuse me. No problem. In particular, white box testing concerned with executing all the instruction or condition, or more generally, execution paths in the unit under test. Okay? If you are in iterative programs, when there exist loops, you normally set a limit on the number of iterations executed in each loop, and this is referred to as the path length. And for instance, path 0 length means that you don't execute the body of the loop, and path 1 you execute once, and so on. In functional programs, you don't have loops. Instead, you have recursion. And if you look in the literature, you don't find many works about what a path means in a recursive program. Then you have to define some criterion on what a path and a path depth mean in a recursive program. And in this work, we define a unit under test to be a collection of mutually recursive functions called from a visible top one. And we propose a definition of path and a path length for that kind of testing unit, and present an algorithm for generating exhaustive set of paths up to a given depth. This work is in the context of our platform called Caveat, that supports functional language as an intermediate representation. And then here you can see a picture of what the platform does. You get a program. Let's see if this works. You see the picture. You get a program in this functional representation, and then our programs, as is a platform devoted to verification, the programs are endowed with a precondition and a postcondition, formal precondition and formal postcondition, and then from there you generate several things. You generate a set of constraints that represent the precondition, a set of constraints that represent the postcondition, and a set of constraints that represent the paths. Then you give this to a SMT solver, and then you get models for these constraints, and these models allow you to generate test cases. These test cases are executed in this right corner by the test driver, and the representation is converted into Haskell in order to execute it, and then the test driver executes the unit and get the result and checks the post condition, gives the result to the SMT solver, and the SMT solver gives you if the test is correct or not, is valid or not. Then in total, the user does nothing, just write the program, write the precondition and the postcondition, and the whole set of cases and the execution validation of these test cases are done on the platform. Then part of the problem is how to generate this white box paths, is what this work is concerned. Then I will describe the functional intermediate representation. Then I propose a graph representation for this kind of programs, and then I present the algorithm. Okay, the intermediate representation is a first order functional language, a kind of core functional language. You have atoms, constant, variables, function application, constructors, tuples, and you have sequential lets, and you have cases with pattern matching and algebraic constructor and so on. And the only construction allows you to define recursion is this let fun, the sentence that allows you to define a set of mutually recursive functions. Okay? This is our language. For instance, you want to program in this language how to insert into an AVL3 an element that will be the shape that has the program. I hope you can follow. If the tree is empty, you just create a node with the element. If it's not empty, you have to decide if you insert to the left or to the right. And after inserting in the tree, you do a balance checking the equal function. The equal function is here. You have to decide, you compute the height of the trees, you compare, you detect a left unbalance or a right unbalance, and so on. Then I only show part of the unit here. Here you can see the complete graph of this problem. The top function that is not recursive, called the insertion function. This is recursive. Then this is called the equal. This is left balance and right balance. Compose just takes two trees and a root and compose the trees. And many of them use the height function. This is the complete call graph for this problem. Okay. Then what is a path here? A static path through a set of mutually recursive functions we define as a potential execution path that starts at the top function and maybe calls some of the mutually recursive functions several times, and after that finish some point in time and produces a result. This is an execution path. And what we generate are static paths. Not all the static paths are feasible because sometimes you traverse contradictory conditions. Then but this is not part of this problem. This is part of the SMT solver that tells you that this path is unfeasible. We generate all the static paths. And then this is a path. And what is the depth of the path? The path we define as the maximum unfolding depth that a recursive function may undergo in the path. The maximum unfolding depth. If you translate, I have not said that in my platform, this intermediate representation is because we transform programs written in conventional languages such as Java and Haskell or a part of Haskell. We convert this to this intermediate representation. Then you have a program with loops. This is translated into tail recursive function calling each other in a circle, let's say. Okay, then when all the functions are tail recursive, that is the typical situation when you translate an imperative program, then depth zero fast corresponds to non-iteration in each of the loops. Depth one corresponds to at most one iteration. This definition corresponds to the usual definition of path in imperative program. But if you have non-tail recursive functions, then the depth corresponds to the height of the call tree deployed during the path execution. Then depth zero means that each recursion function executes one of its base cases. Depth one corresponds to at least one recursive function execute a recursive case, and then this recursive case execute a base case, and so on. Okay. Well, for instance, in the insertion in an ABL3, you have two depth zero paths that corresponds that inserting into an empty tree or inserting a key that is already in the tree. Then you don't have recursion there. Depth one means that you call once to the insertion function calls recursively to insertion function again. And you have to pass because you can go to the left, to the right, or to the left. And then these cases go to has also two paths because has to execute the base case. And you get in total 4 paths of the length 1. Excuse me, there's an error. It's depth 1 there. And you call equal, and equal has also 2 paths, and the number of paths increases exponentially. The more complex is the unit. Okay. Well, then how do we compute static paths in this kind of programs? Well, the first thing is we have to choose a representation. And in iterative programs, it is very easy to represent the control flow chart of the program as a planar directed graph, and then to compute paths there is an easy task. But if the strongly connected components of this directed graph corresponds to the loops, then it's very more or less easy to generate paths there. But if you have a recursive program, you cannot draw this program as a planar graph. It's not easy to do because you have recursive calls, and you will have to unfold these calls, and then you get a graph inside the graph, and the number of unfolding is infinite, it's potentially infinite. Then you don't get a finite graph. It's not easy to draw this. Then what we propose is a graph representation at two levels. At the first level, each recursive function is represented by its control flow graphs, but there the internal calls are not non-expanded, are just nodes. And this is there are no cycles. It is a directed acyclic graph. And another part of the representation is the call graph. Okay, and there you see the whole set of mutually recursive functions. As these graphs are not arbitrary, because if they were arbitrary, to find paths there is not easy. But as these graphs come from programs written in programming language, you can assume some properties. For instance, each strongly connected component in the call graph has a single entry node, because this corresponds that functions has a single entry node, or loops has a single entry node. But as a loop can finish in a strange way, not the normal way, can finish with a break or a continue or an exception, you assume that each strongly connected component may have more than one exit to another node in the graph. And each node in the graph is reachable from the sink. You have a single source node, a single sink node, and each node is reachable from the source, and you can reach the sink from every node, and so on. These are properties that you assume in the graph in order to generate the paths.
You claim that you cannot represent a recursive program
as a single graph, yes.
Yeah, but if you apply continuation passing style to it, then you can represent it as a planar graph.
Even if you have infinite number of calls, yes? Well, if all the functions are tail recursive, of course, you can do that.
That's exactly what.
And yes, you transform to continuation pass style, but then what are you testing is a different unit, perhaps. If you are transforming your program into a different program, are you sure that the paths computes there correspond to the paths of the original program?
Every compiler does this.
Well,
eventually, you convert to continuation passing style.
Well, to transform, I agree with you, but to preserve the number of paths, I am not sure. Okay. Well, then I will explain now how to compute the paths with this representation. Okay, the algorithm. Well, I remind you that a unit under test considers a single top function that is not recursive. From there, you have a let-fun expression where you define a set of mutually recursive functions. And the algorithm has 6 phases. The first one is to compute the control flow graph of each individual function. This has node cycles. Then you generate all the paths in these graphs. We call them template paths. Then we generate the call graph. We split the call graph. This is one of the tricky parts of the algorithm. We split the call graph into disjoint graph, I will explain, and then compute the strongly connected component of each subgraph. And then after that, we compute the paths by expanding the template paths and the strongly connected component. Then I will explain with my example how to do that. Well, the control flow graph is very easy to compute. In every function, you have 4 types of nodes. You have a single source node, single sink node, that is this square and this diamond node. and this node has no code associated to it. The rest are either blocks. The blocks can be conditional. For instance, you have a case, you have a conditional block. You have a sequential of let expressions. You have a sequential block. And you can have also call nodes that are nodes that you are calling a function there. For instance, here you have this ins, that is the recursive call to ins, and after that the call to equal. Okay. Then the template paths are just to compute all the paths from the source to the sink in this kind of graph. We call them template because they contain call nodes that you have to expand afterwards. Okay. These are the two first phases. Then we compute that, the call graph. But the important thing here is to distinguish between tail calls and non-tail calls, because it's not as easy as it may seem at first sight. For instance, equal call the compose function in a tail position, but left unbalance and right unbalance call also the compose function, but in a non-tail position. Then we decide that compose is non-tail, and then all the edges going to it are non-tail, and this is the same for the height function. Why do we do that? Because we have in the next phase we have to split this graph into a set of disjoint graphs as you see here, and the reason for that is that you want to compute execution path of the top function, but if you have a non-tail call, then you have to compute independent paths for this call. You don't have to confuse between the sink of a non-tail function being called and your own sink. Then for that reason, this split means that you have to compute paths in these subgraphs independently. This is more or less the idea. And the essential of this part of the algorithms is that you keep the tail edges of the graph and you discard the non-tail. It's more complex than that, but essentially is what you do here. Okay, then you are prepared to generate paths. And then the next phase is generating the paths in this, starting with this split graph. And then first you have to decide the depth. And the depth at this level means the number of times you touch the entry node of each strongly connected component. If you enter, for instance, in this instance, it's a strongly connected component. If you enter once and go to the sink, then this is a deep zero path. If you enter, 2 minutes, thank you. If you enter once and twice and then exit, then it's a depth one path and so on. This example is very simple, but in principle you can have in a strongly connected component, you can have many functions there. Then the first part, you compute all the paths at depth 1, for instance, from the top function to its sink, and then you get top ins sink and top ins in sink. Let's follow the first one. You have this top ins, and then the next of the algorithm, this is one path that represents a complete execution of the top function. The next of the algorithm expands the call nodes. This is more or less the idea. Then you expand top to the right, and you get the body of top that in fact consists on a call to ins, and you get the sink of top and then the other ins. And then the source nodes are discarded because you don't have code associated to it. Then you move to ins, you expand ins and get B1, B2, B3 and a call to ins, that this corresponds to this path here, to the ins, then to the right, then to the left, then to ins, then to equal, okay? You expand that, and so on. You continue doing this. I don't know if I have spent more time to explain, but the idea is to expand, and in the end you get a complete sequence of nodes that correspond to code in the program. You discard the sinks and here I have depicted how the recursive calls are going there. Okay? There is a call to ints that call internally another one to ints, and you see the two instances there. Okay, we have done this for several units. The first 5 correspond to imperative program dealing with arrays. The last correspond to functional program dealing with trees. And this is the depth of the paths. In the ZABL, only with that one, you get 66 different paths. You get depth, you get several hundreds. But most of them are unfeasible. The only feasible one are 10. You know? Then this path in the SAT column correspond to test cases. Okay? And that's all. I conclude by suggesting that we have described this algorithm, we have applied to several functions, and what is important is that some of the functions, for instance, the quicksort algorithm, is a kind of hybrid program because it has a recursive part, because quicksort is recursive, but has the partition inside. The partition is iterative. And then it's a kind of interesting program because you get paths both for the iterative part and the recursive part. And then a single algorithm suffices to generate exhaustive whiteboard paths in iterative, recursive, and hybrid program. And that's all.